Okay, so now we have the final lecture from Raphael on the cosmic microwave background.
Okay. Yeah, so in the second lecture, we discussed the equations that are solved by the Boltzmann codes to compute the angular power spectra that are shown. There's really a lot more to be said about them to get some intuition about them. The problem is that I also wanted to have enough time to talk about the measurements of the angular power spectrum, parameter constraints, and so on. So I'll include these slides if you want to look at it, because in any case I think it's easier to follow these things if you have some time to look at them. There's also a lot of materials online about it by Wayne Hu, for example. And we also had some brief explanations here by Will, for example, about the acoustic oscillations, and yesterday by Giovanni about the integrated Sachs-Wolf contribution. So I won't talk about this for now. I'll include it in the slides, but the outline for what I'm talking about now is this part. So I'll say a little bit about what's in the CMB beyond primary anisotropies, and then I'll focus on the measurement of angular power spectra and the parameter constraints, and then say a little bit about essentially B-mode search and future CMB experiments. So first, notice that, usually when we say CMB data, the data isn't really just maps of the CMB, but it's maps of the sky at different microwave frequencies. Here are the maps that were taken by the COBE DMR experiment. You see it's a map at 31 gigahertz, 53, and 91 gigahertz. And then just again to give you some idea of how the quality improved, here are the maps from WMAP at 23 gigahertz, which is also called the K-band, the 33 gigahertz, 41, 61, and 94 gigahertz, so significantly better resolution. And then there are the Planck maps from 2013 and then 2015 at frequencies from 30 gigahertz to 857 gigahertz. At low frequencies, we have the low frequency instrument, which is a radiometer, which is very similar to what WMAP was. And then there's the maps from the high frequency instrument. Now, this means in practice that if we actually want to learn anything about the CMB and extract cosmological parameters, we have to understand things like the dust and synchrotron, free emission, anomalous microwave emission. Depending on your taste, this is largely a pain, unless you're interested in the dust. Some people find the maps very interesting because they can learn something about the dust. For me, it's mostly a pain. But it also means the fact that we have these maps at different frequencies, that they provide us with additional ways to probe cosmology. For example, we can learn about reionization, the thermal SC effect, kinetic SC effect, lensing of the CMB. We can use them to study cosmology as well. I won't have time to discuss them in much detail, but I wanted to at least show you a very nice measurement of the thermal SC effect. The basic idea of the thermal SC effect is that you have the CMB photons traveling toward us, and some of them have to pass through these galaxy clusters, and they scatter. Some of them will scatter off the hot electrons in the cluster, which means that so some of them will get scattered out of the line of sight. Some photons get scattered into the line of sight, and on average, this means that you lose some photons at the lower frequency end and gain some photons at the higher frequency end. You increase the temperature a little bit if you want. Well, that's not quite the right way to put it, but you get a Y-type spectral distortion. And so you see that there's a deficit where there's a cluster at low frequencies at 44, 70, 143 gigahertz, where you expect to see the largest decrement. And then you have a frequency where it's 0. This is also why this frequency is commonly chosen as one of the frequency bands in the surveys. And then you see that you have an excess at higher frequencies. So this is a very nice measurement of the SC effect. You can use it to detect clusters, to make maps of these clusters. You can follow them up and confirm them. Just the basic equations that go into it is that the change of the temperature is described by this formula, where y is really the integral along the line of sight of the electron density. So this then is really a measure of the hot gas in the universe between us and the surface of flat scattering, except in practice, if you make these maps, there will be contaminations. But modulo contaminations, this is a map of the hot gas. And so what you can do is you can, after removing other things that contribute, make a measurement of the SE power spectrum, for example, and learn about cosmology from that. The other nice effect that I also don't have time to describe in detail is the lensing of the cosmic microwave background. So you have the last scattering surface, and the photons have to make it to us, and so they will get deflected by a small amount. So the temperature we see in the direction n is really the unlensed temperature displaced by a small amount, given by the integral along the line of sight, or the projection along the line of sight of the gravitational potential. This has a number of effects on the CMB. So first, it washes out acoustic peaks in the power spectrum. This is relatively easy to understand, because if you have something that magnifies one of the CMB fluctuations, it moves the angular power spectrum, well, the CLs, to slightly larger scales or lower L. Similarly, if you have a patch in the sky that demagnifies the CMB, you would move them to slightly higher L. If you're doing the full sky measurement, you're averaging over all of them, and so you're averaging these slightly displaced peaks, which means you're smearing out the peaks at some level. And this is really included in all the analyses, so this would really bias the analysis if you didn't include it. It also leads to temperature 3-point correlations, because there's a correlation between the integrated Sachs-Wolf effect and the lensing. This is also relatively easy to understand. So the integrated Sachs-Wolf effect, as we heard in the talk yesterday, is due to the time evolution of the gravitational potentials. The lensing is due to the spatial derivatives of the potentials, but we know that these are related by the equations of motion, so you get some correlations between them. It also leads to a temperature 4-point function of a specific form that one can use to measure the lensing. And you can, for example, so this is the measurement that's shown by Planck, so you can use it to reconstruct the lensing field and then measure the lensing power spectrum. Here, for some reason, I'm showing you the lensing power spectrum before the lensing field, but you see a very nice measurement of the power spectrum of the lensing. You can also make a map. So this is a map that shows you the projection along the line of sight of all the matter between us and the surface of flat scattering, which is a neat thing. So there's a number of nice things that one can do beyond the primary anisotropies. And as you can see, this is not the map, but the power spectrum is measured at 40 sigma, so there's really a lot one can do with it by now. So now I want to give you a little bit of an idea how a measurement of the angular power spectrum would work, and give you an idea why they have the structure they have, and tell you how you use them to constrain cosmological parameters. So here I'm showing you just simulated maps, because I'm saying it's an ideal experiment, so you assume there's no foregrounds, just CMB. You have a temperature map, Q map, U map, and as we said yesterday, in the ideal case, we'll see how to go beyond the ideal case, but in the ideal case, you just compute the multiple coefficients by integrating your delta t against the spherical harmonics, and then square them and average them to get the angular power spectrum. And similarly, you can derive a ELM and a BLM just the way we had defined them earlier, and go also together with a TLM to CTE, or then compute the polarization power spectra, the EE and BB power spectra. Now, the question is, how do we, once we have these, how do we actually estimate the cosmological parameters in our favorite model? And what I'll do, so my notation will be that the parameters in the model will be denoted by theta. Sometimes I'll drop the vector, so whenever there's theta, it's really a set of parameters, and these parameters will describe the model, so these could be the lambda CDM parameters, omega BH squared, omega CH squared, and so on. but they might also include parameters that control the foregrounds, for example. So they go into the model. And then I'll denote for now the data by D, and then later on I'll be more specific what I mean. I mean, D could be, for example, the ALM, so it could be the CLs, or it could be just the temperature or polarization maps. And eventually what we want to know from this data is what's the probability distribution for the parameters in our model given the data. So this is not something you know how to compute directly, but you can compute it using Bayes' theorem, so you can rewrite it. You can write the probability for the parameters given the data as the probability for the data given the parameters times the probability for the parameters divided by the probability for the data. So we don't typically know this. I mean, we might have prior knowledge about this from a previous experiment, so it's called a prior. But this is something in any given theory that we should be able to compute. So if you understand your theory, you should be able to tell me what's the probability for finding a given realization of the data. So this suggests, because this is something that allows you, you can compute, and it's related closely to what you're interested in, to define a likelihood for the experiment. So we'll only pick this part because this comes from other experiments or from some prior knowledge or some bias we have about parameter or some physical understanding we have about the parameters. So we'll define the likelihood for our parameters just in this way. Now, it's I'll keep calling it L. I mean, also for the simple reason that it's not a probability for the thetas. It's not properly normalized. It's a probability distribution for the data. But once you have a theory, this is something you can, in principle, compute. And we'll see a little bit how this works. So before we look at the realistic case, let's look at the warm-up where we look at just a measurement of the temperature anisotropies. And again, we forget about any foreground, sky cuts, or anything. And I'll drop the T. I'll call just the ALMs, just really are the ALMs for temperature. And then their ensemble average is given by this. So the only thing we need to specify are the angular power spectra, as we discussed before. And then because these guys are Gaussian, and this is an identity matrix here, well, proportional to the, well, along the diagonal identity in M, and then proportional to the diagonal in L and L prime. It's trivial to write down what the probability distribution is that gives rise to this. It's just some normalization factor, and then e to the minus ALM squared over 2CL. So this is the probability for these guys. And the good thing is that in our theory, we should know how to compute the CLs. And so we can define our likelihood in this way. So the theory enters through the computation of the CLs, and then the data enters in terms of the ALMs. So hopefully this makes sense. Alternatively, you can change variables. So here I'm thinking of it really as a probability for the ALMs. Alternatively, you can change variables and rewrite it as a probability. So you see the only thing that enters here is something like the CL, the observed CLs. So you can rewrite it, do a change of variables, and rewrite it as a function of probability distribution for the CLs. And then what you get is a likelihood that looks like this. One point to notice is that it's Gaussian in terms of the ALMs. It's not Gaussian in terms of the CLs. So here for the CLs, for the observed CLs, it's a chi-square distribution with 2L plus 1 degrees of freedom. This will be relevant in a little while. So this is very easy to generalize to polarization. In this case, what you can define is a vector of these ALMs where the components really are AT, AE, and AB, all at some fixed L and M. And then here I'm missing the ensemble average. Here this is supposed to be the ensemble average of these guys. This would be of this form with the correlation matrix given by the matrix that you get from just correlating these guys. In this case, you can write the exact likelihood in a way that's analogous to what we had previously, except now you've traded in the scalar quantities for vectors and matrices. So here you really have the inverse of that matrix to get that back out with the ensemble average. Or you can again rewrite it in terms of the observed CLs and get a likelihood that looks like this. So these are the likelihoods for the ideal experiments. For a realistic measurement, there's a number of things in addition to what we just did that we have to include. So there will be noise of the experiment. The experiment has finite resolution. Typically, we will have pixels in the sky maps. And then we also have to include the masking. Also, I haven't said anything about foregrounds, for example. There may also be relative calibrations and various other real-world issues that you have to include. And for this, for these generalizations, it's now relevant that the likelihoods are Gaussian for ALM or in general in map space, but not for the power spectra, because it means that incorporating any of these effects is much easier in map space. What I mean by this is if you're working in pixel space, you know that you can easily compute the ensemble average of the temperature in pixel I and the temperature in pixel J. It's just your theory computation and then some noise covariance matrix. So this would be the angular correlation function evaluated for the angle between the pixels, for example. And then the noise covariance matrix is something that you have to get from the experiment. So this depends on exactly how you went from the time order data to the maps. The probability distribution that gives rise to this, given that it's Gaussian, is again very easy to write down. So the probability distribution for the temperature fluctuations in the individual pixels is again just a Gaussian probability distribution. And this means that you can write down exact likelihoods in pixel space that take into account all these effects that look like this. And it's clear that this also easily extends to polarization. So in the case of polarization, if you want to include polarization, you just define not just the vector of the temperature fluctuations, but a vector of temperature fluctuations and then Q and U fluctuations, and have a bigger matrix that includes the TQ, TU, and so on correlations. Now, the problem with this is, so if this were something we can easily evaluate, we would be done. This is the exact likelihood, so we can just, assuming that we're in a universe that's Gaussian. The problem is that this is very difficult to evaluate in the experiments we're typically interested in. So high resolution, full sky experiments, because you have a large number of pixels. So you might have something like 50 million pixels in the maps for Planck, for example, and you have temperature and polarization. So you have a matrix, the covariance matrix here would be 150 million by 150 million. You have to invert it every time you want to evaluate this thing as a function of your cosmological parameters, because this is the dependence on theta is eventually what we're interested in. So this is just really not feasible in practice. So what one does to make progress is to use approximations for the likelihoods that are based on the CLs themselves to some extent. So one of the approximations, there's really many approximations, as you can imagine. Everyone who works on it comes up with a slightly different, slightly better approximation to the likelihood. One that is used by Planck, and so that's why is the one I'm mentioning here, is a likelihood in which you just approximate, even though it's non-Gaussian, the likelihood for the CLs by a Gaussian likelihood. And you also don't include the dependence on cosmological parameters when you're computing the covariance matrix, but you're just computing it for a fixed set of cosmological parameters. And ideally, this set of parameters should be close to the parameters that you're interested in. So often this is, for example, an iterative process. So you start computing these covariance matrices for some set of parameters, and then you do your analysis, see what you get out, and then might do another run with the parameters set to the ones you got out of your first run. So you make a iterative likelihoods. The covariance matrix here is just, as I said, this object. I mean, it's the covariance matrix for our CLs. The nice thing about this approximation is that you can compute the covariance matrix analytically, even if you have masked maps and you have noise in the experiment. There's other likelihood approximations that I'm not showing, where you add log normal piece to correct for the fact that this is Gaussian while the true likelihood is not. This is what was done by WMAP, for example. There's also more sophisticated approximations. There's one by Hamimeche and Lewis that I also won't describe in detail, but that's the one that's used, for example, in the bicep analysis. So there's different people use different likelihoods. So now let's look a little bit at what these things look like, so you have an idea of what actually goes in, what's being computed by these likelihood codes. The spectra, what we'll have, or the maps that we'll have, are the underlying temperature fluctuations or polarization fluctuations plus noise in a given frequency band in a given pixel, and then we might mask them. So we have some weighting. This might be either just 0 or 1, which is what was done by WMAP. So you just set it to 1 for the pixels you keep. You set it to 0 for the pixels you throw away. For Planck, these are smooth, so they interpolate between 0 and 1. And this is it's okay in both experiments, but it's important to not use just these 0 and 1 maps in Planck, because there's too many point sources, which leads to aliasing, so you want to make sure you're actually using appropriate masks or weighting functions, and then you get some effective, these are the masked maps at the end of the day. So you just take your initial map, multiply it by something. This sets it to 0 in the regions you don't care and keeps it in the regions you want it to keep it. You can then define these multiple coefficients for these masked maps and compute the corresponding pseudospectra, just the way we defined it for the full sky. But these are, of course, not really directly related to the CLs we're interested in. I won't derive it because it's also a little bit messy, but if you work out the ensemble average of these guys, you can show that it's related to the ensemble average you care about, or the theory CLs, by what is called a mode coupling matrix. And then this comes from the pixelization of the sky. This is a pixel window function. And then these are the beams, which will depend on exactly which detectors you're using. And then there's some noise power spectra. So this is what it looks like. And then the things we're interested in are these. So what you either want to do is just take cross spectra so you don't have to worry about them. Or if you know them, you can move it to the other side and then invert the mode coupling matrix. This is something you can do if you basically can measure the correlation function on all scales. If you cannot, then this matrix becomes singular and you have to bin and so on. But so this is why you see the bins in the smaller sky experiments and not in the full sky experiments. So the covariance matrix, I just wanted to briefly show it so you have an idea of what it looks like. I mean, you can compute it analytically, as I said, and then it has some form like this. This is some sum that, anyway, so there's some mess, but it's analytical and you can compute it, you can put it in the code, and you can evaluate the covariance matrix, and you only really have to compute the covariance matrix once in this approximation for some fixed set of parameters. So what's the problem, as I said, for the pseudo-CL likelihoods is that they're only accurate for high enough multiples, because the CLs obey a chi-square distribution with 2L plus 1 degrees of freedom and are not Gaussian. So it gets better by the central limit theorem. As you go to higher L, it becomes nearly Gaussian, but at low L it's not. So these are really not good likelihoods at low L. On the other hand, the pixel-based likelihoods if we're only interested in large angular scales, we can just degrade the resolution of our experiment and make low resolution maps, and then we can actually evaluate these exact pixel space likelihoods at low L and stitch it together to make these hybrid likelihoods. So this is so this is what's usually done. This is what was done by WMAP, also what is done by Planck, as I'll show in a second. So if there are questions, I mean, you can interrupt as before at any point. So the next question is, once we have these likelihoods, how do we actually find the likelihood as a function of our parameters? Now, one naive guess would be, well, I just evaluate my likelihood function on a grid and just interpolate and I'm done with it. Again, this would be feasible if we had a likelihood that's fast to evaluate, but typically it takes a while to evaluate them, partly because on every grid point, for example, you have to first compute the angular power spectrum.
Sí. Dos.
Okay. Is it? I can use this one. I don't have a. Okay. So yeah, so just briefly in one slide, what the idea is behind these is also relatively simple. So one of the standard sampling algorithms is Metropolis Hastings, and if you haven't played with it, it's fun to just try to implement your own version so you get a feeling for it. So the basic idea behind the algorithm is that you start somewhere in parameter space, so you don't know where you should start. You compute the likelihood at that point. And then you pick a randomly chosen next point, so you just jump in some random direction, and you compute the likelihood there. You check what the ratio is. If epsilon is greater than 1, so if the likelihood is larger, you just keep the next point. If epsilon is smaller, you keep it with probability epsilon. So this gives you something like a thermal sampling. If you look at it, you see that this is like a thermal process, and you just repeat and store all the points. Now, I say with some additional work, this will generate random points drawn from L. I mean, all the points are certainly random points drawn from L, but as it is, they're not uncorrelated, so typically you have to do something to the chains later on, but it's all there in the standard codes. But this is the basic idea. You can, in principle, also, if you play with it, measure the correlation lengths and so on, and figure out how you have to thin the chains for the samples to be independent. But what you can do then is you have a distribution of these things, so you can use it to find either your best fit point, so you just ask what was the point that maximized the likelihood, or you can compute means by just taking the mean over all the points you had. You can compute the error bars by just thresholding lambda and ask what value do I have to choose. So I have 68 or 95% inside the contours. So this is what I wanted to say about these things. I hope it gives you a basic idea, and really, if you haven't used it, as you can see, it only takes 5 minutes to implement, and you can sample some simple probability distributions and see that this actually reproduces what it's supposed to reproduce. So now, using what I told you before, I'll go a little bit into more detail about the Planck analysis and tell you about just the measurement of the Planck angular power spectra. And I thought I would show you the satellite again. So as you know, it was launched in May 2009, and it observed from L2, which is what's shown here. So there's the sun, there's the Earth. The satellite's supposed to be at L2. It's the size of a small car. The mirror is about 1.5 meters in diameter. For the size, it's relatively light. It's only 28 kilograms. And it observed until HFI, so it has two instruments, which are a little bit hard to see. In principle, you can see some of this in the mirror here, but it's not really very easily visible in the image, but has two instruments, as I already said. So there's the high frequency instrument with bolometers, which had to be cooled to low temperatures, and this is it ran out of the helium, so eventually it stopped observations in 2012. The LFI instrument, the radiometers, can observe at higher temperatures, so they observed slightly longer, so there's more data from them. The First data release was in March 2013. There was another data release in 2015. From what I understand, there should be 2 more sets of maps. One is frozen for the analysis that will be public hopefully in June 2016. And then there will be another set of maps that are the best maps that they can do in the time they have, and that will be available for the rest of us to play with, and also the people on the team, obviously, after the official team or the collaboration ends. So as I said, I wanted to focus on the angular power spectrum measurement, and their likelihood is a likelihood just like the one I described, also for the same reasons that I described. So you have a pixel space likelihood for the low L, and fiducial Gaussian approximation for the high L. There are some small differences between the 2013 and 2015 analyses in the sky fractions. As you can see, there's a little bit more of the sky used in 2015 because one is more confident about the understanding of foregrounds. And then there's another change was that in 2013, as you know, Planck only used their temperature data but not the polarization data. So the polarization data at the time was taken from WMAP. Now the polarization data is taken from LFI, and the high L likelihoods also slightly changed. I won't go into enough detail to explain what the difference is between CamSpec and PLIC, but they're both essentially these kind of likelihoods. This was a likelihood based from the group in Cambridge. This is the group in France. The likelihoods, both of them, CamSpec and PLIC, are based on the maps at 100 gigahertz, 143 gigahertz, and 217 gigahertz, and they use the spectra at 100 gigahertz up to about L of 1200. The ones at 143 gigahertz up to about 2000, and then 143, the cross spectrum between 143 and 217, and the spectrum of 217 out to about 2500. Now you might ask why the ranges are different. The ranges are different because the different maps come at different resolutions. So this comes at 10 arc-minute resolution, 7 arc-minute, and 5 arc-minutes. In addition, the noise levels in the different channels are slightly different, and it's chosen so you go until the noise is taking over. So this is 100 gigahertz is cosmic variance limited out to about, well, 1200, and then so this is how it's chosen. There's other things to be said. So there's also cuts at the low L. Just to make the approximation work, it starts with L higher than 50. Then there's questions about foregrounds, because you see that there's a lot of foregrounds at 217 gigahertz. And so CamSpec was slightly more conservative in the sense that it used information only from L of 500 and up. PLIC used all the information from 50 and up and has some template model. If for the large F sky that they have now, the foregrounds, the galactic emission is not really fit by a nice power law or broken power law, but has some features, and those have to then be understood. So the other thing, as I said, or as you saw from the expression for the covariance matrix, you need to compute it, are the masks. What you have to mask is certainly the galactic emission. You can see it by eye. Here, I mean, there's the galaxy, so you have to mask it. In addition, there's point source emission that you have to mask, so you see a lot of little holes. And then there's also a CO emission. That's in principle some of these red regions. So this part here is CO emission, and there's some stuff back here that's also CO emission. That's also masked. Much of it is along the galactic plane in any case. So in addition, there's even though you have fairly conservative masks, there's still residual foregrounds at high latitudes, both extragalactic but also diffuse galactic emission that you have to model. If anyone's interested exactly how this was done, I can say more about it, but for now I don't want to bore everyone with this part. The likelihood is the kind of likelihood I described at high L, so it's an analytic fiducial Gaussian approximation. And the noise, we still need to compute the likelihood, is usually obtained from the half differences, or you take first half of the mission, second half of the mission, take the difference, the signal should be gone, and you can obtain the noise in that way. You could imagine doing simulations or other things, but there's correlations in the data that are hard to model, so it's really measured. And the spectra look something like this. So naively, you might expect some white noise. At 143 gigahertz, you see that it is fairly white on at least scales above L of 400 or so, but there's departures on large angular scales. 100 gigahertz, certainly you shouldn't be treating as a white noise spectrum, and here's the 217 gigahertz spectrum for the noise. So once you plug everything in, compute your covariance matrix with the formulas I showed you, and then run your Markov chains, this is how you get the cosmological parameters. So you get some mean and some error bars from the prescription I briefly sketched, and you see that all the parameters are measured at the roughly percent level, except for the optical depth. So there's still certainly more work to be done to get a better measurement of the optical depth eventually. This is also important for future experiments, because it's a parameter that's hard to measure from the ground, and so eventually the problem will be that one wants to measure the neutrino mass from ground-based experiments, from their contribution to the anisotropies on small scales, or from the lensing, and there's a degeneracy between the neutrino mass and tau. So if you can't measure this parameter, you also won't be able to measure the neutrino mass very well from the CMB. So this is something that needs to be sorted out, but other than that, all the parameters are measured to 1%. It also is interesting to some extent to measure tau better, just because it is degenerate with the other parameters. So if you don't really know what tau is, you also might have a bias in the other parameters. But all in all, the measurements are quite nice. Everything seems consistent with lambda CDM. These tables don't actually look too different from what we had from, let's say, WMAP 9 plus ACT plus SPT or similar data sets. But we have more confidence in them now, in the sense that A, it's coming all from one experiment, and B, that you can look at extensions of lambda CDM, where you, in addition to the lambda CDM parameters, allow to vary the equation of state of dark energy, or you allow a tensor contribution, you allow some running, you change the helium abundance, and so on. And it's really hard to see here, but there's these faint dashed lines that indicate where the lambda CDM prediction is, and you see that the data always, even if you allow additional parameters to vary, always pushes you back onto the lambda CDM prediction. Okay, so this is what I wanted to say about the Planck results. There'll certainly be more to be said. I'm happy to discuss it in private, also in questions, if there's more interest. Now what I wanted to say is a little bit about the B-mode search, and just give an outlook. As I already explained yesterday, these initial conditions for our system of equations that we solved to compute the CMB anisotropies is really set very early on. It's certainly set before the hot Big Bang, so before the universe was first filled with a hot and dense plasma. And so it gives us information about, in inflation, for example, about the inflationary dynamics. It tells you something about the slow roll parameters through the normalization and the shape. So this is the prediction for the delta R squared, the power spectrum of this quantity R that we introduced yesterday, and the prediction turns out to be nearly scale invariant, and it's consistent with what is seen in the Planck data. So the NS has a funny normalization, so NS equals 1 is a scale invariant spectrum. In addition to the scale invariant scalar modes, inflation also predicts a nearly scale invariant spectrum of gravitational waves. And what's interesting about this is that its amplitude is just set in terms of the Hubble rate during inflation, which means that measurement of these primordial gravitational waves would really tell us something about the expansion rate of the universe during inflation, or using the Friedmann equation that I showed you in the first lecture, you can relate the expansion rate to the energy density, and we would finally learn something about the scale of inflation. It's really one of the most basic questions you can have about a physical process, what the characteristic scale is. And for inflation, right now we have no idea, which is a little bit embarrassing, but that's how it is. So the scale in terms of, so you can rewrite this in terms of a tensor to scalar ratio. You can write the energy scale of inflation as 10 to the 16 GeV times R over 0.01. 0.01 is an interesting number because that's something we'll be able to get to over the next few years. And then the 1/4 is a bit of a problem. So if you see something, then you know inflation happened at the gut scale. If you don't see anything, you're not able to really push the limits down significantly because you need 4 orders of magnitude in R for every order of magnitude in the energy scale, and this is just not something that's, you cannot push it much below the gut scale. So it's a somewhat binary situation. Now, one theory reason that makes this interesting is that if you were to measure something, if you have a tensor to scalar ratio larger than 10 to the minus 2, you know that the inflaton must have moved over a super Planckian distance in field space. This was first shown in papers by Leith and independently by Turner. And the interesting thing about it, these super Planckian excursions, is that they're hard to control in an effective field theory. So many of you have probably heard these arguments, so I'll keep it short, but I wanted to briefly give you a short argument why it's hard. So you might consider, let's just forget that we're inflating for a second, just consider a flat space quantum field theory, and let's consider some low energy effective field theory with just one light degree of freedom. And let's imagine we're working at low energy, so we can ignore the higher derivative terms, even though one can in principle include them in the argument. So all I have to specify the effective action for my 1 degree of freedom is the potential. So I have a potential, and it might have a constant piece, it might have a quadratic, cubic, quartic interactions, as well as all kinds of higher order terms, which are typically suppressed by the cutoff and come with order 1 coefficients. Now you see, if you're interested in excursions in field space that are small compared to the cutoff, you only really need to know the first few terms in the potential. If you are interested in excursions that are super Planckian or large compared to the cutoff, then in principle it looks like you would have to know all these terms. So you can ask, well, maybe someone can compute all the CNs for me. Can I then use it? And the answer is you still cannot use it, because this degree of freedom in the absence of symmetries should also be coupled to at some extent to the heavy degrees of freedom that you integrated out to get to this low energy effective field theory. And it might, if it couples, it might have couplings that are either phi chi-squared, where chi-squared is the heavy degree of freedom, or phi squared chi-squared. And the chi-squared also has some mass, so there's an m squared chi-squared term. And you see that if you give a wave to phi that's of order the cutoff, eventually there might be cancellations, and the mass of your heavy degrees of freedom might drop below the cutoff, so you have to include them in the effective field theory. You might also have couplings to other light degrees of freedom if you had other light degrees of freedom to begin with, which means that the spectrum of your effective field theory changes completely as you move over a distance as large compared to the cutoff. This is a simple cartoon example where something like this happens. So you have a phi field and a psi field. This is supposed to show you where the potential is constant. In this direction, you see that psi is quite heavy, phi is light, so you can integrate out psi, and you can start moving, but as soon as you get out here, it's just not described by a single degree of freedom. It's really a two-dimensional problem. So the other guy became light, and you have to include it. Now, a solution, a possible popular solution, is to just use a field with a shift symmetry and then break the shift symmetry in a controlled way. You have to break it because otherwise the field has no potential. The shift symmetry helps because then all the couplings to the higher dimension, to the heavy degrees of freedom, must be through derivatives. And if you're coupling through derivatives, the wave does not affect their masses, and so you're not changing the spectrum as you move your field. you have to break it because otherwise there's no way to end inflation. One simple example of this is just chaotic inflation with a mass that's much smaller than in Planck. In this case, you have just one operator that breaks the shift symmetry. You generate others through loops, but they will be small by the naturalness arguments, the usual naturalness arguments in field theory. Now, in field theory, this is all nice, so we can just postulate that there is such a symmetry, and then we're done once and for all. But it's not obvious that these kind of shift symmetries exist in a theory of quantum gravity, so this is what makes these gravitational wave detections interesting to some extent, that they might actually teach us about shift symmetries in a theory of quantum gravity, for example. Besides that, of course, it would be exciting to just see the quantum fluctuations in the space-time metric. There's also many other implications of these experiments, and so many people, me included, everyone was excited when we saw the bicep maps, and it seemed like there was agreement between the E-mode polarization signal and the simulations that you expect from lensed lambda CDM plus noise, but there wasn't agreement between the B-mode signal and the simulations that you would have expected in lensed lambda CDM plus noise, so it clearly showed that there was some difference and there was some excess B-mode polarization on degree scales. Of course, now we know it's mostly dust, but the maps are still the best maps we have, and we heard a nice talk by Chris Sheehy about it. So at the time, the noise level was 87 Kelvin degrees, which means it's the deepest maps. And if for comparison, the Planck noise levels are a few microkelvin degrees. Now, the reason BICEP can go significantly deeper is just because they look at a small patch of the sky, while Planck spreads out the sensitivity over the full sky. Otherwise, the sensitivities are actually quite comparable. So for me, because I'm interested in the inflationary models and some large field models of inflation, and there was no foregrounds included in the likelihood that was published, I wanted to make my own likelihood that included foregrounds, and so I started trying to use various estimates for the foregrounds, and they all came out very large. And so in the end, I never made a likelihood because it seemed like it might all be dust. And the sad news, I guess, from the Planck collaboration eventually came when they did a measurement in the BICEP2 region at 353 gigahertz and rescaled it, and it was consistent with the excess being all dust. This was consistent with the measurements I showed, which on the one hand I was happy about because it meant I didn't screw up the measurement, but at the same time it was bad because it meant that there was no signal. From an experimental point of view, everything's good because you can use this data now that you know it's dust to put tighter constraints on the tensor to scalar ratio. And to me, it's been a little bit surprising that there wasn't more excitement about ruling out m squared phi squared. It was maybe the best model we had for the early universe, or the most popular for the last 30 years. Now it's gone. So it's a big step forward in our understanding, even though we don't know what should replace it, but we'll see. So there's certainly many models that are still allowed. One thing I wanted to briefly show or explain is that the improvement that you see in this plot looks very incremental. So there was an improvement, there was the Planck data, then there was Planck plus BICEP, and now there's BICEP keck from the most recent papers, and they just slightly decrease the contours in this plane. It looks very gradual, and I wanted to briefly show that this is maybe the wrong way to think about it. To understand this, what you can do is you can show the constraints. So the tensors contribute to the anisotropies of the CMB in two ways. So on the one hand, they contribute essentially a constant on large angular scales to the temperature anisotropies. At the same time, they contribute to the B-mode polarization. The two signals, at least statistically, are independent, so you can make a joint likelihood for them, where you independently vary the tensor contribution to T and BB. So this is not very physical, but it tells you where the constraint is actually coming from. So you can Here, this is the constraint that you get from Planck. It's the upper limit on the contribution of the tensors that's allowed to the temperature, and it is at around 0.13 in this plot at 95% confidence level. And then here, from the B-mode constraints before the BICEP2 announcements were at the level of 0.7 at the 95% confidence level. This was before BICEP2. It was completely dominated by the temperature data, and then there was a huge step forward by BICEP2, in fact, by a factor of roughly 7, an improvement of the measurement of the constraints on the B-mode polarization by about a factor of 7 in the B-modes. It just so happened that the constraints are now comparable from the B-mode polarization and the temperature, so it looks like nothing much happened, but in fact there was a big improvement in the measurement, and the progress is actually fairly rapid. As you can see already, this has decreased even just by adding the new data, so the progress here is fairly rapid, and this is also expected to continue over the next few years, given that there's a large number of experiments that are already taking data and are going online. So we heard talks from some of them here. There's also, these are ground-based experiments. There's also the balloon experiments. Spider flew recently. Piper is something that's an idea that would make maps of the sky of 85% of the sky. And in the future, let's say 5 years and out, there might be the CMB stage 4 experiment that I'll say a little bit more about in a second, which would be a joint effort of the entire CMB community in the US to try to go after B modes and the mass of the neutrinos and effective and dark energy. And then there might be satellites. Lightbird is a Japanese mission that looks fairly good. And then Pixie, you've heard mentioned both by me, by Yassine, in a number of the talks. Now, what makes the quest to see the B modes difficult is shown in this plot. So what we're trying to get to is these kind of blue signals. What we have to struggle with are, on the one hand, there's a contribution from lensing of the E modes into B modes. This is relatively well understood, so in principle you can subtract it. Then there's also the contribution from the dust, and you see it's much higher. This is here the cleanest region of the sky, cleanest 1% at 150 gigahertz. The 150 gigahertz is not the cleanest or lowest for the foregrounds, but I didn't want to have to put the big error bars. So if there's in principle at lower frequencies, it should be a little bit cleaner, but not dramatically. So it will be a challenge to beat the foregrounds. And the problem right now is that we also don't even have tools that are good enough to forecast how well we can do or how the experiments should be designed. So here, this is one way to illustrate it, is you can take the various, your favorite foreground models that we currently have, pick a patch of the sky, look at what the polarization fraction looks like in the Planck maps, look at what the polarization fraction looks like in the various foreground models, and you'll find in the Planck sky model where the small scale structure is added by simulations, it looks completely different. These are different models for the galactic, the smooth component of the galactic magnetic field. They look completely different. You do see a strong dependence on the magnetic field, so in principle one can use the data to improve them, but in any case right now we don't have even models that are good enough to forecast these kind of things. If you take the current forecast seriously for an effective, for example, then the error bars are very nice. So you get error bars forecast for the CMB stage 4 experiment at the level of 2 times 10 to the minus 2. This is the only forecast I'll show because I don't have that much time. But to me it's fun because it's really a way to do beyond the standard model physics with the CMB. It allows you to probe individual degrees of freedom that decouple at very early times from the standard model, and you can find their contribution to the CMB in principle. So they typically, if you have an individual fermionic degree of freedom, you get a contribution of 0.05, for example. So if you want to know more about it, there's a paper that's here, and this is, I forgot to fix, so there's a typo in in this reference here. So that's what I had to say. If there's questions, I'm happy to discuss it more. But I hope you now know a little bit more about the CMB than you did before the lectures. If not, then I apologize. But there's also nothing I can do about it now. So the CMB, as we saw, is a fairly simple system. It's GR coupled to some matter in the linear regime. And as a consequence, I mean, it's easy to understand theoretically. As a consequence, it has provided us with a lot of information about the early universe, and it will continue to do so. We might detect primordial gravitational waves with it. We can measure the mass of the neutrinos, the number of relativistic degrees of freedom, dark matter. Through the lensing, we can put some constraints on dark energy models. And there will be large-scale structure surveys, big new surveys going online. So the next decade should be very interesting in cosmology. So I'll just end it with that.
Questions for Raphael?
So you talked about the optical depth measurement and how it's got fairly large uncertainties.
Yeah.
Planck measures an instantaneous reionization optical depth, right?
Well, not instantaneous, but it assumes some profile and then some delta z. I mean, some width of the reionization of typically 1.5 redshift of. So there's some width that you can adjust. It's fixed to some number. So there's some fixed profile that's being fit.
Okay. So is it observational uncertainties or is it theoretical uncertainties that are?
Oh, it's not sorry?
For the large uncertainties on tau, is it theoretical uncertainties? Is it like?
No. Well, to some extent, one should say that tau really is not a cosmological parameter. I mean, if we understood how the universe got reionized, then we wouldn't have to include it here, and we could just compute it and be done with it. So in that sense, all of the uncertainties are completely on the theoretical side. but that's maybe not the right way to think about it. So these, I mean, here you're assuming that you just cannot predict it at all, and you're just trying to extract it purely from the data. And so these error bars are just the statistical error bars that you get from the data analysis. And what makes it hard is that tau is largely coming from the contribution to the polarization on large angular scales, where the foregrounds are relatively difficult to control, foregrounds and systematics in the experiment. So there's, which are also related. So there's leakage in the experiments, which I can say more about. But that's what makes the analysis, the measurement of tau actually difficult. This is why there's still no measurement from the HFI instrument, because there's a lot of systematics in the polarization data on large angular scales. So on the one hand, I would say, yeah, it's all theoretical, but then there's also difficulties in measuring it. You can also ask, well, is the CMB really the best way to measure the optical depth? In principle, the answer is probably no. So there's also proposals to measure it from 21 centimeter line observations. The error bars naively look much better, much smaller. One of the problems is that the surveys, at least, that become available around the time you would need it for the CMB stage 4 experiment typically go out to a redshift of 10 or so. And if the optical depth really is very low, then we might be lucky, and there might be no ionization above redshift of 10, but it's unclear right now. So there could very well be some contribution to the optical depth, and then you would only get a lower limit on the optical depth from those measurements. So that's the complication with those. So.
Other questions? Okay, let's thank Raphael again.